Good morning, everyone. What a wonderful pleasure to see everyone here, many familiar faces. So indeed, my name is Julian van Velzen. I lead the quantum team at Capgemini. And what I wanted to talk to you today about is a path to quantum value. And perhaps not because I can lay out exactly how that path would look like, but more because it is a very, very challenging topic. It really doesn't look so easy. I think way too often we talk about the applications and how it transforms industries, but we don't really get into the specifics of how that could actually work in algorithms and hardware. But it also goes the other way around. Way too often, perhaps we think about algorithms and about hardware, but we don't really have the end goal, the use case in mind. And I think if we want to make quantum applications work in the foreseeable future, we really have to get that approach together. We have to combine both our thinking about how the use case work in practice with the hardware implementation, thinking very carefully and deep about the use case. And so I think that is the path towards value eventually, and that's really what I want to talk to you about. And I think it's a good moment to start talking about that, because I really think that a commercial, a quantum computer that could be used for commercial application doesn't have to be too far off anymore. It's no longer a sort of exploratory talking. A computer is within sight. We know more or less what it looks like. We know more or less what kind of specifics it might have. And with that, we really have to start thinking about how does this translate into practical applications. And I think on the one hand, we can be very, put confidence in the ambitious roadmaps that IBM provided and consistently over time prove that they can keep up to their promises. And that within this decade, we might see a machine capable of 100 millions of gates. And on the other hand, I think many of us were very pleasantly surprised by some of the results by Q-era and showing that many innovative approaches can still work out and maybe even accelerate the timelines. And of course, there's many other progress happening on middleware and algorithms as well that could potentially accelerate timelines. And so instead of having sort of a more general view, I think it's most important for us to get more specific. What does it really mean to implement an application in real industrial setting? And so if we go to use cases, I think that chemistry really is still our best shot, right? I think that hopefully it's not controversial here, but it really is the one area where we still have a fair chance that there is actually better than quadratic or even exponential speedups. But it's not just that, right? It's also that there is very mature research organizations and brilliant people that know how to connect it with conventional tooling and how to make it work. And it's also one of the reasons where we generally think that there is a need for more compute power, right? Because we know that we won't be able to simulate larger systems in a full accuracy. And I think that would be fine, right? Even if quantum chemistry would be the only thing that we end up using quantum computers for, that could still be completely disruptive against in many industries. And so I really like this quote from Matthias Troyer from Microsoft to show that even if quantum computers would only benefit chemistry and material science, that would be enough. So if we go into that, and I think it's still even for quantum chemistry, it's far from easy. Even for very small systems, if we look at the first plot on the left is for phase estimation, we very quickly end up with massive circuits of hundreds of thousands, even for, in this case, 16 orbitals. Right, and this is vastly beyond the reach of today's quantum computers. And you can see this exponential growth. So if we want to go to systems that are actually of interest, we have to almost increase this by maybe half an order of magnitude. And so you can imagine that this will go way beyond the capacity of our compute systems. But even if we would get these deep circuits to run somehow, maybe with clever tricks and with error correction and mitigation, even then we have to think about does this work? If we think about any real application, drug discovery, where we might need to scan millions of compounds, even these systems might be way too expensive to scan such number of compounds. Or in many cases, it might not be feasible or impossible anyway if we want to think about properties that are actually of interest. It's not just a ground state, or it's not some energy level. It's probably higher level properties like toxicity or reactivity or those type of things, right? So even if we can run deep circuits, we still need to think how we connect this to our other tooling. And finally, even if this were to work and we have deep circuits, we have a sort of an integration with our compute workflow, how do we make sure that it actually is used? And I think one example that is telling is to show that, you know, even though there is these massive AI models that are exponentially growing in size very rapidly, that companies are not able to adopt this. And why not? Because it's just very difficult to actually implement something in a real scenario. And so if we want to avoid that, that this happens for quantum computing as well, we really have to think about all those three stages together to make that work. So that is really the key point that I wanted to stress, is that if we want to think about quantum computing applications in the next couple of years, we need to think about an end-to-end approach where we don't only consider just the hardware implementation and the tricks that we can use to squeeze most out of the hardware. We also need to think very deeply about the use case, how we maximize and reduce the circuit depth and implement it and integrate it with our existing software, and also really about thinking how we can use it for the right applications. And if we think about any of those topics in isolation, it's just not going to work, right? We need to have a combined vision for the three of them. So instead of trying to sketch sort of all the ideas that we have on that, which I think is not going to last in my 10 minutes that I have left, I would also really like to invite you to some of my colleagues that will be focusing on each of those topics. So Francesca, somewhere maybe here in the room, will host a panel on the pharmaceutical industry, really trying to address that. How can we get organizations to think about that path to quantum value? My colleague Sam will talk a bit more about a specific use case that we did with Unilever on how we can predict degradation of esters in a data-driven pipeline. And my other colleague, James, will really talk about how error correction can be used and what companies have to know about that. So I would invite you to go to each of those sessions to go have a deeper perspective on either of those topics. But I think the point is that we really need to have a combined view of them as well to make it work. So I wanted to show just a few examples of the work that we do to combine that, to work on that end-to-end approach. And so the few elements that we need, right? We need a framework where we can minimize the circuit that we need or maximize the circuit that we can run on the computer. We need to think about how we integrate this with existing tooling, and we need a system where we can sort of incrementally build value for applications that are actually of interest. And our approach that we have developed over the past few years is this quantum-centric idea. So we really put quantum at the core in a data-driven end-to-end pipeline. And so the idea is that it really starts with starting to figure out what are really the chemistry reactions that we are interested in. How can we isolate what we can solve with a quantum computer and where we might need a molecular dynamics or a quantum chemistry solver? How can we build different models for different length scales? And then if we have identified that, how can we fragment this small part of a quantum system that we will run on a quantum computer while off-sourcing everything else to classical solvers? And if we have that, if we have this system where we can use quantum simulation at very small length scales, how can we extract features that are then predictive for properties that are actually of interest? So for example, how can we create features from electronic structure of some systems and use that to predict properties of interest for example, drug discovery, material development, or anything else. And so we have applied this method to a number of cases over the past few years. One of them that I would just like to briefly mention is a project we did with Unilever. And so this was really about predicting ester degradation. So esters are the things that provide flavor and in this case for consumer products for Unilever. And what we wanted to do is to think about how can we model this system, how can we derive features from the electronic structure that we can use to predict the hydrolysis rate of these systems. So what we do is we fragment the molecule because it won't be able to simulate this as whole. We really want to focus on the smaller part that is classically difficult. And then derive features, and in this case, bond critical points that can be used for hydrolysis rates. And what we showed was that could be a very effective way of doing that. In this particular project, we worked also with the Prometheum, so with the tool from QCware for a DFT tool, which I think is really showing that you really need to have this end-to-end view where you use both a combination of quantum resources as well with classical resources to build an end-to-end pipeline. Another project that where we applied these same ideas are really to find applications for battery research. And so in this project, we tried to identify what are really the interesting chemistry in battery design where a quantum computer could be valuable. And batteries are interesting for a whole number of reasons. They have these massive design space. It's for a good reason that even though we do loads of research, sometimes still a Tesla explodes. And even though we found out about lithium metal, it takes decades to produce them at scale. And so we really want to be able to speed up that process. And again, it's not so easy because we know that there is these interesting chemical reactions. There are these transition metals who are not so easy to calculate or to simulate. And so a quantum computer may be interesting here. And so one of the use cases that we've worked on is to see how we could simulate electrolyte decomposition on cathode materials using a combination of classical solvers with quantum solvers to build sort of a hierarchical model for different solvers where we can build molecular dynamics to simulate the environment and simulate the effect of different additives in the fluids with a classical solver such as DFT in combination with a quantum solver. Maybe one more example that I wanted to show is about a project we did with GSK. And this was all about trying to predict reactivity of covalent drugs. So we applied the same ideas as I described earlier. So really trying to obtain features from, in this case, dynamical features. And if I was hoping there would be video, but it doesn't matter so much. But if we, in the picture that I wanted to show is we give this electron a kick, see what happens over time, obtain features from that system, and then use those to correlate them with structures, right? So again, we apply the same ideas of using quantum simulations at small scales to predict properties of interest. So what we have here is a framework to think about how can we use applications, a quantum computer in sort of end-to-end approach. But of course, still we need to really very carefully think about how can we maximize the circuits that we can run. And so one of the ways which we try to do that is by seeing, can we use some of our chemical knowledge to reduce the circuit depth? And one of the ways is to, for example, truncate the Hamiltonians that we use. And what we found is that very often, if we only keep the biggest parts, we still get very accurate answers. So what you see here is that if we cut a very big part of the Hamiltonian, we still have good results. And in this case, the results vastly degrades over a longer period of time. But if we only look at the first initial time steps, we actually get pretty good results. And of course, this is a trade-off, right? Because we introduce extra approximations. But I think will be very important in the future is that we always have to make trade-offs, right? We always will be limited with the hardware that we get, at least in the foreseeable future. And so we have to make very careful choices to get most out of the hardware for the best applications that we can use. Another final example on how we try to use these ideas of squeezing most out of the hardware for very specific cases and making applications work is a project where we did on error mitigations protocols. And the key idea here was that very often these error mitigation protocols work by using knowledge from the hardware that we have, noise models, but don't really use the domain knowledge that we have. So if we have any type of information about our system that we may be able to use for a specific error mitigation protocol, we can further refine our statistical analysis and get more out of the hardware. And so ultimately, in the end, the goal is to leave nothing on the table, right? We want to make sure that we really squeeze out everything that is possible, combine our efforts on the hardware implementation with the insights that we have from the use case for the relevant application. And if you don't use a combination of those three, it's just not going to work, at least, I guess, in a foreseeable future. So maybe in 10 years from now, we'll be able to use software out of the box and it will just run and it compiles and be fine. But for a very long time, we'll have to get into that level of details, that specifics, to make it work. And so that's really what we try to do at Capgemini. Not necessarily building our own product or our own IP, but really trying to get the best solutions together from all of you guys, basically, from all of the software and the middleware and the hardware together, to bring them together and to work on a path towards creating some of the applications that could actually work in the next years. And so I already mentioned a few companies that we work with. We try to do that in other consortia as well. So, for example, one project was with for a Horizon Europe project where we worked together with Airbus, Pascal, and many others to bring them all together for real applications. Finally, I mentioned already some partners, the ones here, but also the work we did for Unilever with Prometheum, the work with GSK with Q-Control. But I also have another announcement that we had, is that we had this week was quite a last-minute struggle to get it done before the conference, but a partnership with Pascal. So I'm very happy with that, and also an investment that we did in Pascal through our investment venture fund. And I'm very happy with that because I think Pascal is really one of the leaders in the neutral atom technology space. And given our history and our common roots here in Paris, I really think that we can push the field further together. So with Pascal, but also with many of the other partners and clients here, I'm really looking forward to bring it all together and to build the best technologies together to make these applications work. Thank you.
Thank you, Julian. And time for a question or two. One question is, most of your chemistry applications appear to be rate-based optimizations.
What's right?
Rate-based optimizations. Have you done, here's the real question, have you done any work modeling molecular states specific to drug reactions?
So I'm not 100% sure. I think the best way to answer the question would be my colleague Sam during his presentation later today at, if we go back, it's done. I think at 2:30.
Okay.
So, but anyway, drug discovery is a big field. One of our topics has been predicting reactivity for covalent drugs. So that's definitely a big area. Yeah.
Right. It sounds like kind of an insider specialist question. Please check the agenda for the other talks by Capgemini. Follow-up question here. What's the size of the Capgemini quantum team and where are they based?
So it's a global network. Within the team, there is about 40 people or so, full-time equivalent people. But then what we rely on is really our big organization that has long history with clients in drug discovery, in battery development, in many of the topics that I showed. And so what we try to build on is our quantum team that focuses on really the quantum side of things, but then combine that with our domain knowledge that we get from the other teams. Okay.
One last question. Do you have any plans to try the quantum error correction experiments in the near future?
So, yes. So again, there will be one panel for my colleague who will talk about quantum error correction.
Okay.
And I think for any application to work, we need to think carefully about the combination of error correction, error mitigation, and other techniques. Mm-hmm. And so absolutely that will be part of the program to get that to work.